Today we're looking at the paper Toward Efficient Agents, a survey of memory, tool learning, and planning by Xiaofeng Yang and the team from Shanghai AI Laboratory. And here is the reality check for everyone in the field. We've moved from static LLMs to agentic systems. We're talking POMDPs with tools and memory. But while effectiveness is way up, efficiency is now the absolute bottleneck. These systems are recursive, they loop, they're expensive, and they lead to massive latency and token bloat that just kills production deployments. This paper breaks down the solution into three critical components. First, memory, how we compress and manage it. Second, tool learning, minimizing how often we call tools and cutting latency. And third, planning, controlling the agent's search mechanisms. The goal here is to move past just making smaller models and instead optimize the entire agentic workflow. It's about finding that sweet spot, that Pareto frontier between cost and task success. If you're an ML engineer trying to deploy agents without, banknoting your entire inference budget, this is the survey you really need to understand. Okay, let's really unpack this. We're looking at a survey from, early 2026, and honestly, it feels like it arrived just in time.
Oh, absolutely.
I've been seeing so many demos lately that are incredibly impressive, but, they take 45 seconds to respond to a simple query.
Right.
It feels like we've built these Ferraris that can only drive in first gear.
It's a classic engineering pendulum swing, isn't it?
Yeah.
If you look at the evolution map the authors provide, you see it. We went from the stone age of CNNs and RNNs, moved into the golden era of pure LLMs, and now we are firmly in this agentic era. But the rules of physics or the rules of compute have completely changed.
Right, because with the standard LLM, it's all linear. I ask, what's the capital of France? It computes, it answers, done.
Exactly. It's a single inference pass.
Yeah.
But an agent is recursive. The paper defines it formally as a POMDP, a partially observable Markov decision process.
And that partially observable part is key, I think.
It's everything. The agent doesn't know the state of the world. It has to go find it. So it loops. Plan, act, observe, update. That loop.
Yeah.
That loop is where your wallet goes to die.
And that's the distinction the paper makes right away. You're not just paying for intelligence anymore. You're paying for the process of finding the answer. They list 3 specific costs that are killing deployment.
Yep. Inference latency, context window saturation, and just excessive token consumption.
And context saturation is the silent killer, isn't it? You think, Gemini or GPT-5 has a multi-million token window, I'm fine.
You're not fine. Filling that window slows down inference quadratically in a lot of architectures, or at the very least adds significant linear latency.
So this paper isn't just about model compression, right? We're not just talking about quantization or pruning weights.
No, and that's why I like this survey so much. They define efficiency at the system level. They talk about finding the Pareto frontier. Basically, you have 2 options. Maximize intelligence for a fixed budget, or minimize the budget for a fixed level of intelligence. If you're just throwing a 100 billion parameter model at every single substep of a plan, you are nowhere near that frontier.
So to get us there, they break it down into 3 pillars: memory, tool learning, and planning. Let's start with memory, because in my experience building these things, this is where that context bloat really happens.
This is the most obvious bottleneck.
You have an agent running for 3 days, and suddenly the history is 50,000 tokens long.
Exactly. The paper distinguishes between working memory and external memory. Think of working memory as your RAM, what's in the context window right now.
And external memory is the hard drive.
Right. Vector databases, logs, long-term storage, all that stuff.
And the challenge is getting the right data from the hard drive to the RAM without just overflowing it.
Precisely. And doing it without losing the semantic meaning. The paper highlights a pretty neat technique called recomp.
Retrieve, compress, prepend. I love a good acronym. But walk me through the compress part. Because when I hear compression in language, I worry about losing the needle in the haystack.
Totally.
If I compress a legal document, do I lose the one clause that actually matters?
That is the risk. And Recomp handles it by splitting compression into 2 types: extractive and abstractive.
Okay, what's the difference?
Extractive compression is basically like using a highlighter. It keeps the exact sentences from the retrieved documents that are most relevant and just, discards the rest. It preserves the raw data.
Got it.
Abstractive compression is more like having a synthesizer read the document and then write a summary of it.
So abstractive is riskier. The model is, in a sense, hallucinating a summary.
Technically, yeah, it's generating new text. But Recopy combines them. You extract the key evidence to make sure you have factual grounding, and then you abstract the context to save tokens. You prepend that hybrid summary to your prompt.
So instead of pasting 10 pages of documentation into the prompt, you paste a paragraph that captures the essence and the specific 3 sentences that prove it.
Exactly. It bounds the context. The paper is basically arguing that we need to stop treating the context window as this infinite dumping ground.
Just because you can fit a book in the prompt
Doesn't mean you should.
They also talk about how to manage this memory. There was this section on the append versus overwrite dilemma. This feels like a database problem.
It is, 100%. If you just append every single interaction to your history, you eventually crash the system or you confuse the model with like irrelevant noise from 3 hours ago.
Yeah.
You need operations like delete or update.
But who decides what to delete? If I have to ask the LLM, hey, is this memory important? Isn't that just another expensive API call?
You hit the nail on the head. That's the LLM-based management trap.
Yeah.
It's smart, but you're burning tokens just to manage tokens.
Right.
The paper highlights that efficient agents are actually moving back to cheap keyword-based matchers for memory retrieval.
So good old-fashioned search.
Pretty much. Use a cheap, fast algorithm to find the relevant memory template or chunk, and only then do you bring in the heavy LLM to process it.
Right.
You don't use the CEO to file the paperwork. You hire a clerk.
I like that analogy. Okay, let's move to the second pillar, tool learning. Because an agent without tools is just a philosopher, right? It can think, but it can't do anything.
Exactly.
But calling tools APIs, database queries, is agonizingly slow.
Network latency is the physical limit we can't really optimize away easily. The paper traces the lineage back to toolformer, but the focus now is all about minimizing tool invocation.
Why call the weather API 5 times when once is enough?
Right. But there's a much cooler, more tactical development here that the paper calls out called Tiny Agent. And this is specifically for the edge computing crowd.
I saw that. How does Tiny Agent actually work? Is it just a quantized 7B model or something?
It's a bit more sophisticated. The problem with running agents on the edge, like on your phone, is that even a 7B model can be slow if you're loading it constantly for complex reasoning. Tiny Agent uses semantic routing to specialized, fine-tuned small models.
So instead of one generalist brain, you have, what? A specific little brain just for checking my calendar.
Exactly. You fine-tune a tiny model specifically on the function calling syntax for your calendar API. It doesn't know how to write poetry, it doesn't know quantum physics, but it is incredibly fast and accurate at generating the JSON needed to add an event.
Yeah. And it handles the tool use locally.
Locally.
That's huge for privacy, too. If my calendar processing happens on my device, I'm not sending my schedule to the cloud.
And it solves the latency problem. No round trip to a data center. The paper really suggests this edge-cloud hybrid is the future of efficient tools.
They also mentioned the LLM compiler. This sounded like it was addressing the blocked process problem.
Yeah. This is for when you really do need the big guns in the cloud. Typically, an agent operates serially. Step 1, get data. Wait, step 2, process data. Wait, the LLM compiler tries to turn that into a directed acyclic graph.
Okay, English, please.
Think of cooking dinner. You don't boil the water, wait for it to boil, put the pasta in, wait for it to cook, and then start chopping the onions.
Right, no, I chop the onions while the water boils.
Exactly. That's parallel execution. The LLM compiler analyzes the user's request, figures out which tasks are independent of each other, and just fires off those API calls simultaneously.
But getting an LLM to recognize independence seems tricky. How does it know that chopping onions doesn't require boiling water?
That's where the compiler part comes in. It's a pre-planning layer that maps dependencies. If it gets it right, you reduce the wall clock time drastically, even if the total compute is the same. You're compressing time.
There was also a mention of an economic framework in here, the cost of pass.
Yes. We're seeing this shift to explicit economic terms. Cost of pass literally measures the financial cost of the decision to use a tool.
So the agent is basically asking itself, is the information I get from this API call worth the, 0.002 cents it's going to cost me?
Agents are starting to budget, and they have to. If you want these things running 24/7 as autonomous assistants, they cannot spend $5 to schedule a meeting. The paper argues efficiency is no longer just about speed, it's about unit economics.
Which leads us directly into the third pillar. Efficient planning. This is the brain of the agent. It decides the sequence of steps. And honestly, this is where I see agents fail the hardest. They get into these loops of death.
Yeah, loop of death is painful. You ask an agent to debug some code, and it tries the same fix 10 times in a row, paying for the API call every single time.
So how do we optimize the brain to stop doing that?
One method they mentioned is trajectory optimization. The paper cites a method called trial and error.
Trajectory optimization sounds like physics. Are we calculating missile paths here?
Close. Think of it more like muscle memory for reasoning. When you first learn to tie your shoelaces, you think about every loop and pull. It's slow. It uses a lot of compute. After you've done it 1,000 times, you just do it.
So the agent remembers the path of thought that worked before.
Exactly. The agent explores, it fails, and it learns. But crucially, it stores a successful trajectory in memory. If it encounters a similar problem later, it doesn't replan from scratch using expensive reasoning tokens. It retrieves the successful path and executes it.
It's caching the plan. That seems so obvious, yet most agents today start from a blank slate every time.
And another technique is pruning. This is classic computer science tree search. If you view a complex task as a tree of possibilities, an inefficient agent explores every single branch to find the best solution.
Which takes forever.
Right. Efficient planning uses heuristics to prune or cut off bad branches early. If the agent realizes, oh, looking up a recipe isn't going to help me fix this Python bug, it stops that line of reasoning immediately. It doesn't waste tokens exploring it just in case.
And they also mentioned parallel task planning here, too. Is this different from the parallel tools we were just talking about?
It's slightly different. Parallel tools is about firing API calls together. Parallel task planning is about decomposing the problem itself. It often involves collaborating models.
So like a squad of agents instead of one genius.
Yes. Instead of one giant GPT-4 model trying to be the project manager or the coder and the QA tester sequentially, you spawn 3 smaller, cheaper models. One plans, one codes, one tests. They work in parallel where possible.
It mimics how a software engineering team works. You don't have one person doing the back end, front end, and design sequentially. You do them in parallel and merge.
And usually 3 specialized mid-sized models are cheaper and faster than one massive model trying to context switch between all those personas.
So efficient planning is really about thinking harder so you can act fewer times? Or maybe thinking smarter.
That's a perfect summary. It's trading compute time during planning for reduced execution time in the real world. Because real-world actions API calls, waiting for user input, are always slower than neural processing.
I want to talk about how we actually measure this. The paper covers benchmarks, because my worry is that if we optimize for speed and cost, we just turn the agent into a moron.
That's the effectiveness first view the paper really insists on. An agent that costs $0 but fails every task is not efficient, it's useless.
Right. I saved you money by not doing the work.
Exactly. So they look at benchmarks like SWE-bench, which is currently the gold standard for software engineering agents. It's brutal, real GitHub issues.
I've played with SWBench. It is incredibly hard.
And for efficiency, the metric isn't just, did it fix the bug? It's, did it fix the bug and how many tokens did it burn? We're moving toward a ratio metric, success rate per dollar.
Okay, this all sounds great. We have compressed memory, edge tools, pruned planning, but surely there's a catch. The paper makes it sound like we've pretty much solved efficiency. Where does this break down in the real world?
The authors are actually very honest about the gaps. They point explicitly to LLM-based agents, multimodal large language models.
You mean agents that can see?
Yes. Processing text is one thing. Processing a video stream of a user's screen to navigate a GUI. That's a data fire hose.
I can imagine. If I'm feeding 1080p screenshots into the context window every 5 seconds, Recomp isn't going to save me.
No. An image tokenizes into hundreds or thousands of vectors. The efficiency research for multimodal agents is, and I quote, relatively underexplored. We don't have good compression for visual memory yet.
So if I want an agent to watch me code and offer help, we're still in that expensive and slow phase.
Very much so. That is the next frontier for 2026 and 2027. We need to figure out how to let an agent remember a video without actually storing the video.
It's interesting looking at the date of this paper, January 2026. It feels like we're on the cusp of agents becoming a utility.
We are moving toward what the paper calls long-term sustainable and equitable accessibility. That's a mouthful, but it implies something massive.
What does that mean, practically?
It means if agents remain this expensive, only big tech companies can afford to run them. Efficient agents democratize the technology. If you can run a helpful agent on a consumer GPU, or even a phone like Townie agent suggests, that changes the power dynamic completely.
It stops being a cloud service you rent and starts being software you own.
Exactly. And that's why this survey is so critical. It's not just optimizing for the sake of optimizing, it's optimizing for ubiquity.
So to wrap this up, let's recap the holy trinity of agent efficiency, according to Yang and the team.
Number 1, efficient memory. Use techniques like Reconde to compress history and use cheap keyword matching to retrieve it. Don't use the LLM to manage the filing cabinet.
Number 2, efficient tool learning. Move execution to the edge with specialized, tiny models, and use compilers to run tools in parallel. Don't wait for the water to boil before you start chopping the onions.
And number 3, efficient planning. Use trajectory optimization to remember what worked before and prune the search tree so you don't go down rabbit holes.
I want to leave our listeners with a final thought. We talk about the Pareto frontier. Where is all this eventually going?
I think we're approaching a point where the cost of the agent becomes the primary constraint on its intelligence. But consider this, the ultimate efficiency isn't acting faster, it's knowing when not to act.
The lazy agent.
The smart lazy agent. Are we designing agents that are smart enough to look at a user request and say, you know what? You don't need a complex plan for this. You don't need a tool. The answer is 42.
Yeah.
The next step in efficiency is silence. The ability to bypass the agentic loop entirely when it's just not needed.
That is a fascinating thought. The best agent is the one that does the least amount of work to get the job done.
Precisely. Efficiently lazy.
I love it. It's a fascinating look at where we're heading. Thanks for breaking this down with us.
My pleasure.
We'll see you next time on AI Paper Podcasts.